Assalamualaikum warahmatullah. We now move to the new topic. It is about comparative studies and also the concept of derivative. Do you know what does it mean by comparative studies? Technically speaking, if you look at any mathematical economics books, each of them would say that comparative statistics is the comparison of two different types of economic outcomes before and also after a change in some underlying exogenous parameter. Okay, so that means in a very simple way, there must be a factor which is exogenous, okay, that will affect another variable. Okay, if that factor changes by, let's say, a unit, what would happen to another variable? Would it increase or decrease? Okay, so this is a very simple way to understand comparative statistics. In other words, it compares two different equilibrium states, yeah, after the process of adjustment, if any. Okay, but if we are talking about comparison here, there will be another question. Does comparative statistics also analyze the motion towards equilibrium and the process of change itself? Okay, so can you figure it out? The answer for this question. Now, what's the example of comparative statistics in a very simple way if we want to use economic examples? There are a lot actually, and in fact, you have learned most of them in Principle of Micro at least. Okay, so for instance, let's say investment demand increases. Okay, then we know that in the study of economics, at macro level, this finally will affect income. Okay, usually it will increase income because you have this equation y equals to aggregate expenditure. That means it implies y equals to c plus I plus g. So I here is investment demand. Obviously y will increase, and then in the middle here there are some process, and this process you have learned in Principle of Macro. Now, what happens is that if investment increases by 1 unit, okay, we want to see the direction of income. Income increases or decreases. But based on the theory that you have learned in macroeconomics, it will increase, isn't it? So we want to see the direction of this variable, call it income, after a change in exogenous variable, which is investment demand. Okay. So here we want to see the direction of income or the direction of y after an increase in investment by 1 unit. 1 unit could be 1 billion, 1 trillion, and whatnot. It depends on the measurement that we talking about between these two variables. All right. So, but then another thing that we want to know is that what's the nature of comparative statistics? Is it qualitative or quantitative? You look at the example that I've explained to you just now. I said to you, if investment demand increases by 1 unit, income will increase, isn't it? So we here want to see what happens to the direction of income. Okay, in this case, this kind of comparative statistics, because we just want to look at the direction of income after the change in investment demand, then this kind of comparative statistics is what we call qualitative comparative statistics. You can expand further the question by saying, if investment demand increases by 1 unit, 1 billion or whatever, how much will be the change in income or GDP of a nation? How much? Okay. Then by asking how much, then we are looking at the magnitude of change in income. The moment we want to look at the magnitude of change in income, okay, then we can say that this kind of comparative statistics is actually quantitative comparative statistics. Why? Because it involves a number. By how much is the change in income if investment demand changes by a unit. Okay. Now, if we look into detail about comparative statistics here, then it has something to do with what we call rate of change. I'm sure you have seen the term of rate of change in the previous chapters, isn't it? Okay. Now, the rate of change that you have learned in previous chapter is basically nothing else but the slope. Okay. And the slope, of course, has a relationship with derivative. This one, we can see it later. All right. Now, I want to show you more about the concept of the rate of change. So let's start with a very simple generic function here, y as a function of x. So we call it expression 1 or equation 1. Okay. Our main objective here is to look at the rate of change in y after a change in x. Okay. The rate of change in y by how much y changes after x changes by a unit. Okay, so when we talk about this in the comparative statics context, y in this case is actually the equilibrium value of endogenous variable, and x is a parameter of exogenous variable in the model. Now, if you look at this term, like I said just now, y will represent the equilibrium value of endogenous variable. Why we call y as endogenous variable? Because y depends on x, and you can see clearly x in the equation or system. And the second bit here, x is a parameter of exogenous variable in the model. X is the factor, but this factor, do you know what can affect x? You don't know because you can't see what can affect x in equation 1. Therefore, x is exogenous variable, okay, because the factors that can affect x is not in the equation. All right? Now, so here, we want to look at the concept of rate of change, and then this one can lead further to another different concept. We call it the difference quotient. Okay, let's look at this one by one. So let's rewrite here. Okay, we have initial function y as a function of x, call it equation 1. Okay, now let's say we have one value of x. Okay, we call it x naught. With this x naught, using function of x in 1 here, it can be transformed into y and call it y naught. Okay, and we know that y naught is a function of x naught, isn't it? Let's take another value of x. We call it x1. x1 can be transformed into y1 using function of 1 here. That means y1 equals to fx1 in it. Okay, so here, let's say initial x is x0, the new x is x1. Let's say x changes from x0 to x1. Okay, so when x changes from x0 to x1, therefore we can have something like this. Call it change in x. What is change in x? Change in x is x1 minus x0. Okay, let's call this expression equation 2. Similarly, because x changes from x0 to x1, then obviously y has to change from y0 to y1. Therefore, we can also have this change in y equals to y1 minus y0. Let's call this expression 3. Okay. Recall back, like I said to you just now, y0 as a function of x0, y1 as a function of x1. So here, if you look at 3, actually, change in y can be rewritten as what? Change in y can be rewritten as fx1 minus fx2, isn't it? Alright? Now, could you realize that, okay, if we have fx1 and we know that change in x is equals to x1 minus x0, then from 2 here, okay, from 2, we can have something like this, yeah? So, from change in x equals to x1 minus x0, this implies that x1 is actually what? x0 plus change in x, isn't it? Thus, okay, let's call this 3a for instance. Okay, so fx1 here can be rewritten as what? Using 3a, fx1 can be rewritten as f x naught plus change in x, isn't it? Okay, now look at expression 3 that I have shown you earlier. Let me use different color of pen, let's say blue. Okay, so we can rewrite 3, okay, 3 can be rewritten as the following. So we have change in y, okay, is equivalent to y1 minus y0. And from here we can apply change in y equals to fx1 minus fx0. This one I have shown you earlier, which is this, yeah. And from here, change in y equals to fx0 plus change in x minus fx not in it. Okay? And we know that when we talk about the rate of change, it is a slope. We also know that the slope based on your basic maths in your high school is actually change in y over change in x. That's what you understand, isn't it? Okay, so that's what you understand here. Okay, so from here, remember we have all of this. Okay, let me highlight it. We have this, right? Okay, and then we have this, isn't it? Okay, so we can have something like this actually, right? So we can have something like this. Change in y over change in x is actually equivalent to, remember, we did say that fx1 minus fx0 over, okay, x1 minus x0, isn't it? But if we use whatever we have here, then we can rewrite it as the following. This implies change in y over change in x equals to f in bracket x0 plus change in x minus f x0, isn't it? And over change in x. Okay, because change in x is x1 minus x0. Now, class, how do we call this expression? In the lecture note, you can see that the number of this expression is 5. Okay, and here, okay, is different number that I'm using. You can always refer to lecture note. The number is a bit different, but anyway, the sequence is the same of process is the same. But anyway, okay, so how do you call expression 5 here? This is what we call difference quotient. Okay, so this is what we call difference quotient. It basically talk about if there is a change in x by 1 unit, change in x leads to change in y by how much? Okay, so this is average change in y for every unit change in x, and we call it difference quotient. Okay, so here, this is what I said to you just now, but of course the numbering is a little bit different from here, isn't it, starting here? Okay, but all the process is the same. Now, and then we come to this point, isn't it? And then I told you that this is actually what we call difference quotient. Okay, so difference quotient, what it can do is basically we want to see what happens to the change in to y if there is a unit change in x. We here from difference quotient, we can see the direction of change in y due to the change in x by 1 unit, and also not only the direction of change in y, but also how much is the change in y due to a change in 1 unit of x. Or in other words, we can see the magnitude of change in y if there is a change in x by 1 unit. Now let's have numerical example. We are using expression 6 here. Let's say y as a function of x such that 2x squared minus 1. The question says, find the difference quotient for expression 6. And then once you find the difference quotient, then you need to evaluate it when x0 is 4 and also change in x is 5. And then after that, you need to interpret your results. Before we go to the exercise, let me show you one correction here in this example. This is just a notational correction. You see, change in y equals to fx1 minus fx2, isn't it? It shouldn't be fx2 here. It should be fx0. That's all. Okay. So I'll erase it so that we can see clearly. Should be fx0. All right. Now, let's go to the numerical example. Like I said just now, again, I repeat the question. The numerical example gives you this expression in 6, and then you need to find the difference quotient expression for 6. And then after that, you evaluate your answer when x0 is equals to 4 and also change in x equals to 5. After that, you need to interpret your result. Okay, let's do it one by one. Okay. Let's rewrite again the equation. Expression 6, yeah? So y as a function of x equals to 2x squared minus 1. Okay, so this is 6. But we need to find the expression for difference quotient, and we know that difference quotient is written as change in y over change in x. Okay, so here, what we need to do, let's do it one by one. So we have 2x squared, and x squared here becomes x0 plus change in x and square it, isn't it? And then minus 1. Okay, and then minus 2x0 x0 square plus 1. Okay, and divide all of this by change in x. Now if I use a different color of pen because I just want to show you what is this. This one is particularly fx1, isn't it? Now this one is actually fx not after we open the bracket. That's why you see plus 1 here, not minus 1. Is it clear? Now what we can do here is that if you see the first bit of numerator here, you can see x0 plus change in x squared, isn't it? What can you do with this? You can actually expand it. So it becomes, okay, let me use a proper color, which is black. Okay, so this implies that change in y over change in x can be further expanded as this. 2 times x0 plus change in x, and then rewrite again x0 plus change in x. Okay, change in x here, close bracket, and then minus 1, don't forget, and then minus 2x0 square plus 1. Okay, and rewrite the denominator as change in x. Alright, now expand it even further, we can get something like this, change in y over change in x equals to 2x0 square plus 2x0 change in x, isn't it? This is just a simple calculus. Change in x, the whole thing here, square, isn't it? And then close the bracket. And then minus 1 minus 2x0 square plus 1. And don't forget, divide by change in x. Okay? So from here, change in x, expand it even further. you can get 2x naught square plus 4x naught change in x plus 2 times change in x square minus 1 minus 2x naught square plus 1 divided by change in x, isn't it? So what you can see here is that this one gone because this one means minus and this one also gone. Now we can rewrite it even further as change in y over change in x equals to 4x naught change in x plus 2 change in x square over change in x, isn't it? What can we do next? You can see clearly from the last line here, you can see the common factor. What is the common factor? The common factor is 2 change in x, isn't it? So we can factorize it even further. So let's factorize it. So when we factorize it, it becomes like this. So here, change in y over change in x is equals to 2 change in x, 2x naught in bracket plus change in x, isn't it? Over change in x. Okay. What can we do here is that, because this one is change in x, you can slash it, it becomes 2 change in x, isn't it? I'm sorry, you can delete this. So it becomes change in y over change in x equals to 2 times 2x naught plus change in x. Okay, now, so this is basically the expression for difference difference quotient for expression 6. All right. So let's see. Once we have this answer, we need to evaluate it when x naught is equivalent to 4 and change in x equivalent to 5. Now evaluate at x naught equivalent to 4 and change in x equivalent to 5. So what do we need to do is very simple already. We just need to substitute x naught equals to 4 and change in x equals to 5 back into this difference quotient. So here it is, change in y over change in x equals to 2 times 4 in it plus 5. Okay, so here it shows you what? 2 times 8 plus 5 equals to 2 times 13, finally equals to 26. So that's it. All right. How to interpret this result? What does it mean by, difference quotient here is equivalent to 26? That means the average rate of change in y for every unit change in x is actually 26 for expression 6. All right? So we have seen it in the form of maths here or calculus. Now, if we try to put it in the form of graph, okay, this is just a simple, graph here. Let's say y here and x is here. Okay, so it can be any kind of curve, but this doesn't really reflect expression 6, yeah? Okay, this is just for you to understand how y and x moves from one point to another point. So let's say here, we have this kind of function. Let's say this one is y as a function of x. And I give you a generic function rather than, using expression 6, yeah? Okay, so let's pick one point of x, the initial point, call it x naught. The corresponding y is actually here, y naught. And y naught here is actually fx naught, isn't it? Okay, so let's pick another point, call it x1. Okay, so x1 here, the corresponding y is y1, which is fx1. And I did mention to you, let's say x changes from x0 to x1. Therefore, this one is change in x. As a consequence, x1 can also be rewritten as, okay, x0 plus change in x, isn't it? And because of that, therefore, fx1 here can also be rewritten as f x0 plus change in x. So basically, this one is change in x, isn't it? I'm just rewriting it again here. And this one is actually change in y. So if we have change in y over change in x here, then we have what we call difference quotient. Okay, difference quotient. Quotient because it is a ratio. Okay, so I hope this is clear for you in the form of graph. Now, let me emphasize one thing before we proceed to the concept of derivative. What you can see here is that I'm sure some of you have seen this in business math, but it's not as detailed as this. In business maths or any lower level of mathematics, you can see that you were only required to calculate slope, for instance, and given the numerical expression, you are required to calculate the slope. But here we go into detail about the concept and the theory of slope itself, and then from here you can see clearly. Right after this, when we talk about derivative, you can see clearly the difference between derivative and also difference quotient. Later on, you can see another different concept, but it has something to do with derivative and also difference quotient. Okay, so we have continuity, concept, we have differentiable concept and whatnot. Okay, so please learn this bit by bit and thoroughly, because the main objective here is to show you the difference between all of these. And you can see that in your high school, all of these are called slope, but when you study in detail from scratch, then you can see that there's a slight difference between these different terms, or sometimes it's even significant difference between, each and every single, terms used to explain the slope. Okay, so take note on this seriously. So now we move to the next concept. We call it, not this one, but the new concept here, we call it the derivative and also the slope of curve. We have found the answer, for example, just now. If we don't delete change in x here, then we have change in y over change in x equals to 4x naught times change in x plus 2 change in x squared over change in x, isn't it? But if we simplify it, then this one becomes what? 4x naught plus 2 change in x, isn't it? Why? Because we cancel out the common factor, which is change in x. Now, like I said just now, we want to talk about the concept of derivative. And I'm sure all of you have heard the term derivative before, at least when you learn business math maths in your first year. But just imagine the change in x here is very, very small or infinitesimal. Then what happens to expression 7 here? Okay, so the first thing that we need to do is to simplify expression 7. We have done it, and it becomes 4x naught plus 2 change in x. So we can still see the existence of change in x in 7 after we simplify it. Now, if change in x is very, very small, then we can say that change in x approaches 0 in it. So if change in x becomes very, very small or infinitesimal or approaches 0, then the question is what happens to this term? Yeah. So as change in x approaches 0 also, then what happens to this term means what happens to the whole thing here? What happens to the difference quotient? So how can we present the answer? So we know that as change in x approaches 0, then change in y over change in x becomes what here? Okay, change in y over change in x. Look at the answer here. If this one approaches 0, almost 0, okay, almost 0, this one is not equals 1, this one is like this, a Tindall sign of equal sign, then change in y over change in x approaches 4x naught, isn't it? Okay. Another way to look at it is actually, okay, when we say change in x approaches 0, that doesn't mean that change in x here is actually equivalent to 0. It's just approaching 0, okay? We are not talking about this. Okay, we talk about change in x approaches 0. We're not talking about this. It will not be 0, but it approaches 0. Then, what happens is that the implication is that the whole value of 4x naught plus 2 change in x, okay, will approach the value of 4x naught, isn't it? Because this one, okay, is, relatively equivalent to 0. That means change in y over change in x approaches, 4x naught also, isn't it? Now, or another way of looking at it is basically we are looking at the limit of change in y over change in x as change in x approaches 0. That means we are looking at the limit of 4x naught plus 2 change in x as change in x approaches 0. And then the answer for this limit is actually 4x naught. Okay, so this is another way of looking at it. So here, what we have done here is actually what? So this is actually this, okay? I've shown you this, I've also shown you this. So what is actually 8 that I have shown you earlier? 8 here is similar to this, yeah? Okay? What is actually 8 here? Okay, so expression 8 here or equation 8 here is actually the limit of different quotient. Okay, now here the limit of different quotient, because change in y over change in x itself is different quotient. Okay, I did introduce to you different quotient in the previous section, but then when we take the limit of difference quotient, then we get something like this, isn't it? And another way to call it is what we call derivative. Okay, so the limit of different quotient is actually derivative. Okay, so what does it mean here, class? If this one change in y over change in x is actually, the difference quotient, but if you put limit of change in y over change in x as change in x approaches 0, this is derivative. So these two, a and b, are actually not the same thing, isn't it? A is difference quotient, b is the limit of difference quotient or derivative. But what you did understand from your first year is that there's no difference between these two, because this is just for simplification of the beginner, of the students when they study maths and also economics. But now when you study specifically mathematical economics, you should know by now that there's a difference between these two. Okay, the first one here is, like I said just now, difference quotient. The second one here is the limit of difference quotient when change in x approaches 0. Here, the change in x in A, yeah? I'm talking about A or difference quotient. The change in x here, we don't make it, approaches 0. The change in x here is by a unit or by 1 unit. But here, in B or derivative, the change in x here is very, very small. It's even smaller than a unit. Okay, so that's the difference between derivative and also difference quotient. So be careful when you use these two different things. So when you have change in y over change in x, it's not called derivative anymore. It's just called limit of difference quotient. But when you put limit here and then change in x approaches 0, then that one is what we call derivative. Now, so we have found, we have seen the process of finding the derivative for, expression 6 just now. All have been explained just now. But there are some, very important terms that you need to understand here. So look here, we have primitive function, we have derived function, and C, we have derivative value. So what is primitive function in our, analysis here? Primitive function is the original function. In our case here, let me use different color now. So primitive function is y as a function of x. what is the derived function here? Derived function here is the derivative function. So y prime equal to x prime. This one is the derivative, isn't it? Or dy over dx, isn't it? Now, what's the derivative value? The answer for this in our case here is 4x naught, isn't it? Okay. So, could you see the difference between difference quotient and derivative? I did mention to you specifically that now you cannot say that the change in y over change in x is a derivative anymore, but it is just the difference quotient. The derivative has to be the limit of difference quotient when x change in x approaches 0. Now, the next thing is that when we talk about derivative, do you know different ways of writing the notion of derivative? I did mention to you the method here. Okay, there are also some other ways of writing derivative. I want you to find it, try to learn different ways of writing it and what does it mean. You need to know. Okay, so the next thing here is to show you the process of derivative and how it can be related to the slope of a curve, because all this while when you study about derivative and the slope, it is the same thing. That's what we understand. But is it the same thing or not? So this is the thing that we want to see in the next section. Let's look at the derivative and how we can relate it with the slope of a curve. So let's say we have this expression as expression 9, C as a function of Q. So C here refers to cost and Q here refers to output. And we know that the basic concept of cost, the first one is marginal cost. Marginal cost is actually the change in total cost due to a change in output by 1 unit. So in this case, I'm sure you have seen this. When we talk about MC in the previous studies of intermediate, micro, macro, and whatnot, then you saw this change in C over change in Q. Okay. So in this case, the change in quantity of a product is discrete. Okay. And then if you have this kind of thing, if you can recall back the previous sections, this one is actually difference quotient, isn't it? So what about the derivative then? So we are talking about if the change of quantity of the product, which is Q, is continuous variable. Okay, then the MC here has to be, the derivative instead of difference quotient. So that's why we need to understand the concept of slope of a curve. Yeah, in this case, cost curve. Okay, and if we use the slope of the curve, then this is basically the graph method of the derivative. Okay, or the geometric counterpart of the derivative. So both of them, whether it is a mathematical part counterpart or geometric counterpart, both of them are considered marginal in the study of economics. So let's say we have this kind of graph. Yeah, this is the frame of graph that we want to use. So the cost is here and quantity is here. Okay, so let's say the cost function looks like this. So here is a curvy cost. It's not a straight line cost. Okay, and so we want to use this cost function to analyze the concept of slope and its relation to derivative. Yeah, so cost function here is a function of Q. Okay, so let's say we pick one point on the cost function and consider that point where we have quantity is here. Okay, let's call this point A, and then if we drag down the line until it hits the horizontal axis, then the quantity here, let's say Q naught, and the cost here will be C naught. Okay, so this is the initial point at A, the starting point. Now, let's say quantity of output increases in the production process from Q naught to, let's say, Q2. Okay, and let's say Q2 is here. So if you drag up the dash line, it will hit the cost function somewhere here and call this point B. And at B, the cost value will be here. Let's call it C2. All right. Now, you can see clearly here, there is a change in quantity by this much, isn't it? So let's call this change in quantity as, delta Q. Therefore, we can clearly see that Q2 is actually Q naught plus change in Q. So what happens to the cost here? Cost has increased, isn't it? And the increase is by the difference between C2 and C naught. So we have here change in C. Therefore, C2 here can be rewritten as C naught plus change in C. Okay. Now, the next question is, what happens to this? Change in C over change in Q. When, quantity increases from Q naught to Q2 and cost has increased from C naught to C2, we are talking about movement from point A to point B on cost function. So what happens to this? So here, the change in C over change in Q is actually can be defined as C2 minus C naught over Q2 minus Q naught, isn't it? And basically, if we draw a straight line that passes through point A and B, then this change in C over change in Q is actually the slope of line AB, isn't it? So this is basically the slope of AB. And here, if I write it this way, so let's say we have this. Okay, call this point E. The slope here can be rewritten as EB and over AE in it. Okay. Now, let's consider another different situation. Let's go back to Q naught. Okay, and C naught. Let's go back to point A. Now, I want to use different pen, for instance, blue. All right. Let's say instead of increasing to Q2, Q naught increases to Q1 and such that Q1 is between Q naught and Q2. So let's say Q1 is somewhere here. Okay, so let's say Q1 is this. So if I drag up the line until it hits the cost curve, then the cost will be here at C1. So here, we can see clearly that Q1 is greater than Q0 but less than Q2. Okay, and at the same time, C1 is greater than C0 less than C2. Alright, so it's logic. The more we increase the production, the more cost we have to incur. Alright, then I'm talking about what point here, call this point D. So we can have another calculation of slope when quantity of product produced has increased from Q0 to Q1 instead of Q0 to Q2. And that increase can lead us to another new calculation of slope. And this is referring to a slope line AD. Let me redraw it again, yeah, to make it nicer. So we draw a line that passes through A and D. Okay, let's redraw it again so that it looks nicer. Okay, so line AD. So here, slope of AD is actually C1 minus C0 over Q1 minus Q0. Another way to write it is, let's say this point F, then we can have dF over AF, isn't it? Okay. Now, can you see here when quantity increases from Q0 to Q1, that means we have smaller increment in output because Q1 minus Q0 is smaller than Q2 minus Q0, isn't it? So the increment in quantity is even smaller now. Okay. Next, what if we try to reduce the increment in output even smaller? Okay, I mean the change in output even smaller than Q1 minus Q0. In this case, let's say I use different pen, I use red pen. Alright, now that means we are talking about the increment in output is actually smaller and smaller and approaches zero. The change in output is actually approaches zero. Okay, then here, let me show you. Then we're talking about the change output initially at Q0. Then the change in output is very, very small, such that the change approaches zero. Okay. Here, what we can say is that we can have the concept of limit, which will be explained more in a later section. But anyway, what happens to the slope of, of the line at this point, at point A? Okay. So let's say this line, red line, here is the line of KG. So if I draw like this, let me draw it properly, then I can have this, yeah? Because we want to see what happens to the slope. And let's say this point H. Okay. So we know that the initial point is Q0. Okay. Here, the line of KG, as you can see, is a tangent to the cost curve at point A, isn't it? It becomes a tangent line of cost curve at point A. And at the line of KG, okay, the change in Q approaches zero because you can see that it's actually exactly at point A and the change in Q is almost zero at Q0. Okay. From here, we can calculate the slope of KG is actually what? GH or HG, GH or HG over KH. Okay. And this slope is actually this one, yeah? Okay. Actually represents limit of change in C over change in Q as change in Q approaches zero, isn't it? Now, this is what I mean. So, if we have slope of Kg, which is equivalent to GH over KH, this one is actually representing the limit of changing C over change in Q as change in Q approaches zero. Alright? In where the initial quantity is at Q0. So here, the slope of cost function, okay, at point A, at A actually refers to what? Refers to the derivative value of f prime q. Alright? So can you see here, the main idea about the slope in relation to derivative is that the slope, when you initially calculate it, okay, from one point to another point, where change in Q is still positive, bigger than zero, then you can have slope like this. But as you reduce the amount of change here, initially the change is from here to here. Secondly, the change reduces from here to here. The next one, the change is here, almost zero, isn't it? It becomes smaller and smaller. Okay, so what you can see here is that as the change in Q or output becomes smaller and smaller, okay, the slope here at point A, or the slope of line KG, which is a tangent to cost function at point A, okay, is actually HG over KH, and this slope at point A, okay, represents the derivative of cost function. Okay, so this is how a derivative can be explained in the form of graph. Now, why don't you try another point? Let's say you pick this point and choose another second point and calculate the slope, and then reduce it, the change here, you reduce it until you have the change in Q approaches zero. Would it be the same concept? Okay, so I hope you can try it at home also. Now, what we need to do is that after we understand the concept of derivative using graph, we need to look into detail more about the concept of limit. As we can see here, as the change in Q becomes smaller and smaller, okay, the slope of KG here is actually the limit of change in C over change in Q as change in Q approaches zero, isn't it? Or in other words, the slope of KG here is actually the limit of difference quotient for cost function as, change in output, approaches zero. And the slope here or the limit here is actually the value of derivative at point A, and the limit here or the value of derivative at point A is actually f prime q, isn't it? Or CQ prime, C prime. All right. So let's move to the concept of limit. We already know that from the previous sections that when we have limit of different quotients, so if we have limit of difference quotient like this, okay, as change in x approaches zero, then that means this is actually derivative, isn't it? Right. Okay, so here, because it has so much, in terms of relationship with derivative, then we need to look at the concept of limit in detail. Okay, so for simplicity, let's say we use what we call shorthand symbols, then we don't have to write very, tedious symbols like this. Okay, so let's say we have Q equals to change in Y over change in X, or Q itself is different quotients, okay, and change in X is written as V instead. So we can have something like this: dy over dx equals to limit of difference quotient as change in X approaches zero, or because change in Y over change in X is Q and change in X is V, then we can rewrite it as limit of Q as V approaches zero. Okay, so remember, yeah, like I said earlier, derivative heavily related to the notion of limit. So that's why we need to learn the concept of limit in detail. Now, the next thing that we need to know is that when we talk about concept of limit, then we have to look at the limit from left side and also right side. So now we are talking about the left side limit and also the right side limit. Listen to this carefully because perhaps it sounds so abstract, but it's not actually, yeah? So let's say there is a value of a variable named variable v. So we have variable v here, okay? And this v approaches a specific value, okay? And it approaches a specific value, let's say 0. Okay, it can be any other value as well, but let's say it approaches 0. Now, if v approaches 0, the next question is, what will be the value of Q? So Q, what happens to Q? Okay. Listen again. As V approaches 0, what happens to the value of Q? Okay. If you listen to this kind of statement here, don't you think that Q here depends on V? Because the way I asked it, when V approaches 0, what happens to Q? Is there any impact on Q or not? then if that is the case, then could we say that, okay, Q is actually a function of V, okay? And here, in this case, our main objective is to find the limit of Q as V approaches 0. Okay, we want to find the limit of Q as V approaches 0. Okay, what's the limit of Q as V approaches 0? Now here you can see that V approaches 0, so we have specific number that is 0. Okay, alright. But we can also find the limit of Q, okay, as V approaches certain number, you know, it can be 0 and any other number, call it N. Alright, so an N here is basically finite real number. So in this case, in our previous example, which is this, okay, N is what? N is equivalent to 0, isn't it? Okay, now, so here, let me erase some, some mess up here so that I can have some space to write. Okay, so here, when we have V approaches N, okay, we need to find the limit of Q, isn't it, as V approaches N. N could be 0 or any other, finite real number, okay? So when V can approach the number of N, then it can approach from left or right. You get what I mean here, okay? So if V can approach number N from left side, okay, then what happens to the limit of Q? Okay, limit of Q, what's the value, isn't it? So that's the question actually. Okay, so here, let me repeat again. If the variable V can approach the number of N from the left side, then Q can approach a finite number. Let's call that finite number as L. L can be 5, can be 6, whatever it is, depending on the, a function. Okay, and then in this case, L is the left side limit of Q, isn't it? Because we are talking about V approaches N from the left side, then Q approaches number, call it L. Then that means that L is actually left side limit of Q. Now, how do we write it in mathematical symbol? Then we can say something like this. Limit of Q as V approaches N from the left side. Now, from the left side, you put minus sign as superscript. Okay? So, minus sign here means approaches from 0. Approaches from left. Okay, but then, okay, if we talk a different way, if the variable V can approach the number of N from the right side, then from the right side, Q approaches a finite number of L. So that means in mathematics, okay, it can be rewritten as limit of Q as V approaches N but from the right side is actually L. Okay. Now, the first one here is also L. Okay. Alright. So what does it mean here? Limit of Q from the left side is L. Limit of Q from the right side is L. Because limit of Q exists from both sides, then we can say that limit of Q as V approaches N exists, which is L, isn't it? Okay. So here, let me summarize it. The idea is, in order for you to know whether the limit of Q exists or not and equivalent to L or not, then you have to check, the existence of this limit of Q when V approaches N from left side and also, right side. If the limit of Q from both sides exists and it is equal to certain real, number like this, let's say L, then we can say limit of Q as V approaches N exists. Okay, so like I said just now, I check the limit of Q as V approaches N from the left side, then I found the answer L. But I also need to check from the right side. Okay, positive, then the answer is L. Therefore, from here, I can say that the limit of Q, okay, as V approaches N without any sign on superscript is equivalent to L, because it exists, the limit exists from both sides. Okay, so here, but then what happens if L here, like I said to you, L can be any number, isn't it? Finite real number. But what happens if the answer, instead of L, we found answer like this? Look at expression 12 and 13. Limit of Q as V approaches N is equivalent to infinity. Infinity is not a finite real number, because infinity is the opposite of finite, isn't it? Infinite is the opposite of finite. Okay, so if you look at 13 also, limit of Q as V approaches N is minus infinity. So in this case, what happens is that, 12 and 13, there is no limits. Okay, for 12. There is no limit for 13. Okay, so in this case, in certain cases, there is only a limit on one side that need to be considered. What does that mean? Okay, so this is another case that we have to take into consideration. Then we need to look at the graphical illustration to make to get more understanding on this. So let's have the first illustration here, graphical illustration. So we have this. Let's say we put Q on the vertical axis and V on the horizontal axis, and our graph looks like this, for instance. Okay, so let's pick one point. Let's say this point. At this point, we have value V, that is N, and the corresponding Q is here, and we call that Q as a specific value of L. And if you look at the curve drawn here, in the first one, we call it graph A or curve A, then you can see the curve is drawn smoothly, isn't it? So let's find the limit of Q when V approaches N from both sides, left and right. Okay, so here, limit of Q as V approaches, N from the left hand side. Okay, left hand side goes to the N value here. So what happens here is that then this one going up here, isn't it? So we're talking about moving towards this point. Okay, and in this case, limit of Q as V approaches N from the left hand side is L. And what about if we approach N? If V approaches N from the right hand side, so what's the value of Q in this case? From the right hand side goes to the left, V approaches N, and then from here goes down here. That means Q, limit of Q when V approaches N on the right hand side, from the right hand side is L also. So limit of Q as V approaches N from the right hand side is L. So in this case, limit of Q as V approaches N, okay, without putting plus or minus sign because it means from both sides is equivalent to L. Then that means for this curve, the first one, the smooth curve, limit of Q as V approaches N exists, that is L. Alright, what if we have another curve, and this curve we have Q also on the vertical axis, we have V also on the horizontal axis, and the curve looks like this, for instance. Okay, and at this point, let's say this is N value and this is L value. It is very clear that from this curve we can see a king point here. Okay, if you don't remember what does it mean by king, I'm sure you have learned, in oligopoly microeconomics, you have king something like this, remember? So P is here, Q is here. Alright, anyway, let me erase that one first. So let's go back to this example. So in this example here, we can see that we have sharp turning point when value of v is at n and value of q is at l. Okay, so let's check whether this graph or this curve has limit or not when we approaches n from both sides. Okay, so here this is b, yeah. Okay, so limit of q as v approaches n from the left hand side. The left hand side is here, going this side, so going up like this, isn't it? And the answer is L. Okay, and what about if we check it from the right hand side? As v approaches n from the right hand side, which is here, then this one going here, isn't it? Then you can make this point. So here, limit of q as v approaches n from the right hand side is also L, isn't it? So what can you say here? Although we have sharp turning point when v is equivalent to n at this point, we can still find that limit of q as v approaches n from both sides is L. The limit still exists because the graph here is continuous, although we have, at this point it's still continuous, okay, but it's not smooth, okay, it has sharp, turning point here. Okay, so that's the second example. What if we have another example? Let's do it in the next slide. So let's say this is C. Okay, so we have Q here and we have V here. Okay, so how does the graph look like? So let's say it looks like this, and then suddenly jump and get the lower value like this, and at this point we have n, and here at this value we have L1, and at this value we have L2. This one should be dash, yeah, because it's not a curve. It's just to label the L2. Alright, now here let's check whether this kind of graph has or curve has limit or not. So let's check from both sides. Limit of q as v approaches n from left side. From left side is this, going to the right approaches n. Then you can see that it's actually, limit of q when v approaches n refers to L1 here. Alright, so it's equivalent to L1. What about from the right side? Move here. Then we're talking about this curve, isn't it? Okay, we're talking about this curve. So you can see here, limit of q as v approaches n from the right hand side is L2. And L1 is here, L2 is here. So can we say that limit of q as v approaches n exists? No, because L1 is not the same as L2, isn't it? So in this case, in the third case here, graph C here, the curve here you can see is not continuous at when v is equivalent to n. Okay, and therefore when we try to find limit, it doesn't exist because at n we have two values of q, L1 and L2, and you can see here the curve jump from this line to this line at v equivalent to n in it. So that's why this curve is what we call step function or step curve. Okay. Now, for instance, if I give you example, okay, what's the application of step function? Let's say V here is the amount of expenditure for the pollution abatement, and Q here is the pollution level, for instance. If you talk about any V value below n, so n becomes threshold in it, below n, then you can see that the level of pollution is very high, which is L1. But if you spend more V or spend more money for pollution abatement, remember V here is pollution abatement cost, then the level of pollution falls, from L1 to L2 as long as the value of V is greater than N here. Okay, so this is an example of step function, in the study of environmental economics, for instance. You can also use other examples to, of step function in economic study and also in other types of study. And all of this can be found from, journal articles, basically. Okay, so that's example is C. What if we have example in D? Okay, here, same, we have Q on the vertical axis, we have V on the horizontal axis. So let's say I divide the first quadrant into 4 different smaller quadrants, and the most left here, the bottom left, then we can have something like this, for instance. Okay, and the upper right here, we can have something like this, for instance, and N is here, L is here. So the same thing that we need to do is that to find the limit as V approaches N from left and right. So let's say we talk about limit from left. So limit of Q as V approaches N from the left side is what? From left. Then we are talking about this curve, isn't it? You can see that the value of L going down further and further, and could be negative as well, and then it becomes negative infinity. Okay, what about from right? From right, moving from here to here, okay, then we are referring to this curve, isn't it? And you can see as V approaches N, L increases further and further and further and becomes positive infinity. So limit of Q as V approaches N from right side is positive infinity. Now you can see here from left and right, it doesn't give you the same answer of limit of Q in it. So what can we say here? Limit doesn't exist. Okay, limit doesn't exist. It's very clear that, minus infinity is not the same as infinity. So limit doesn't exist. Here is one example. So basically, the graph here shows you two curves of hyperbolic curves. All right, and this, uh, hyperbolic curves are actually between asymptotes. Okay, this is asymptotes here. All right, so these are the graphical illustration of limits and its existence. So let's look at the evaluation of limit. This is some example here. I won't discuss all of them. I expect you to do the rest, but I picked let's say number 3 here. We have, if you see the exercise here, find the limit of Q as V approaches minus infinity. That's the first one. The second one is find limit of Q as V approaches 2. And the third one is find limit of Q as V approaches positive infinity. So how do we solve this? I'll show you for this, and I try to solve for this only, then you can try the rest. So here, limit of Q as V approaches positive infinity, okay, what happens here is that is equivalent to limit of what? Limit of 1 minus V square over 1 minus V as V approaches infinity, isn't it? Before you put the value of infinity to the expression here, you need to check whether this expression can be simplified further or not. Now you look here. Actually, the numerator, not the denominator, the numerator here we can factorize it even further. This is what I mean. Limit of V as approaches limit of Q, which is written as 1 minus V square over 1 minus V, can be further simplified as this. Okay, this is approaches. So here 1 minus V, 1 plus V, isn't it? Over 1 minus V, isn't it? Okay, is it clear? Now remember, the condition is that V cannot be equal to 1, because if V equal to 1 here, then the denominator becomes 0. Okay, and can't be solved. Alright, now anyway, if you look here, you have common factor, cancel out. So you are left with limit of V approaches infinity, limit of 1 plus V as V approaches infinity. Now because V is defined as infinity, then you can start solving it. limit of 1 plus infinity as v approaches infinity is actually infinity. Don't miss any single step here, yeah, because when we talk about limit, it's not the same as finding, final answer of differentiation, in which you can skip some little step. But in limit, you have to show every single thing here, because the process here, we need to see how do you find the limit. The process is very important. Now, why don't you try for, this and this for third question, and also this for the whole, three questions here, yeah. So this is an example of evaluation of a limit, and try to do exercises in the textbook, and also try to find, exercises from the internet. There are abundant, questions of limits, evaluations of limits that you can find from the internet, and you should do it. Don't wait until last minute, yeah. All right, so that's the evaluation of limit, and we have done, a little bit about the concept of limit, but then we haven't done it formally. So now we need to look at a formal view of the concept of limit. So we want to analyze the concept of neighborhood. Let's say we take a number, call it L, yeah? So I put it in the form of a line like this, so that, it's much easier to show you in the form of illustration. After that, then I can show you in the form of formal graph. Okay, so let's say I get a number, call it L, and L is situated here. Then, let's say there is another number, call it A1, such that if we have L minus A1, then L minus A1 must be less than L. L is here, so L minus A1 must be less than L. Where is it on this line? Let's say somewhere here. L minus A1. Okay, so here is very clear that L minus A1 is less than L. L can be any number. Okay, so number A1 is actually this, isn't it? A1. Okay. Now, let's say we have another number, call it A2, such that when we add A2 to L, then L plus A2 is greater than L. So on this line, if it is greater than L, it must be somewhere here in it, to the right of L. So we have L plus A2. So here is what we call A2. So what about number that falls between this, range? Okay, then there are a lot of number that falls between this range, isn't it? Then we have the set of number falls between, okay, L minus A1 and also L plus A2, isn't it? So this is basically interval. Okay, so when we talk about intervals here, number 1, 2, and 3 here are the terms that are related to all of what I said just now. So when we have interval, another thing is we call it closed interval, and half open and half closed interval. So if we have closed interval, yeah, let's say we have L, and then we said that L is between, 0 and 1. Okay, so it can be rewritten as this as well, greater than 0 or equal to 0, but less or equal to 1, isn't it? Okay, so this is closed interval. Closed means what? If you see here, close a rectangle, okay, so 0 is included, 1 is also included. Okay, what about, if we have something like this? If we have, let's say I write it here, L is a subset of between 0 and 1, but then if we can write it in another form, it is actually greater than 0, less than 1, it doesn't include 0 and 1, isn't it? Okay, this is what we call open interval, and when we have open interval, then it doesn't include the, lower, boundary and also upper boundary of the interval. In this case, lower boundary is 0, upper boundary is 1. What if we have half open or half closed interval? Let me write it here. Let's say L is between 0 and 1. That means L greater or equal to 0, less than 1, isn't it? Okay. Now, in this case, I can also rewrite this as this. L is actually, this and 1. Okay. So this is another way of doing it. This is half open and half closed interval. An example, yeah. Now, all of this symbol, actually, you can learn it by yourself by looking at the resources from the internet, because there are a lot of symbols of mathematics that you can refer to from the internet on how to write it properly here. Now, let's go back to this. Let me erase the mess here. If you look here, so let's go back to this concept of neighborhood L here. Okay, so how do we define the neighborhood of L that we have talked about just now? So neighborhood of L is actually an open interval which is defined as this. Look here, it is between L minus A1 and also L plus A2, isn't it? And it also, doesn't include L minus A1, also L plus A2. And remember, L here is actually the value of Q. So here, the neighborhood of, L, which is between L minus A1 and also L plus A2, is also identified to the set of Q evaluated at Q between L minus A1 and also L plus A2, but it doesn't include L minus A1 and L plus A2. This is an open interval. Okay, now let's go back to this before I forget. Yeah, if you look at this and also this, okay, here the first one here doesn't include 0 and 1, isn't it? Upper boundary and lower boundary. And this is what we call strict inequality, very strict, okay, because it doesn't include, that's why it is called closed interval. But here, it includes, you can see equality sign, therefore it is called weak inequality. What about this? This is a strong, strong inequality or strict inequality. Okay, so now the next thing that I want to show you is to understand the concept of neighborhood, for L using a diagram. So let's say we have this frame of diagram, and we have, as usual, Q on the vertical axis and V on the horizontal axis. And let's say our curve looks like this. Okay, so here Q is a function of V. Okay, so here we know that if we go back to expression 11, we know that from 11 says what? 11 says that limit of Q as V approaches N is actually L. Yeah, so I've written 11 here. Let's say we take, an arbitrary neighborhood of L. Okay, so here, but the first thing, let's say we pick one value of V, and that value of V we call it N. Let's say we take one value of Q, and that value of Q we call it L. Okay, now remember, I want to explain to you about the concept of neighborhood using diagram, because it has something to do with the concept of limit. Okay, so we have L for Q, we have N for V. So let's take an arbitrary, neighborhood of L. Okay, when I say take, neighborhood of L, it is an interval, and that interval must, includes L here. Okay, so look at the vertical axis here. So let's say that interval here looks like this. So we have L minus A1 below L, and here L plus A2 above L. Then we draw a dashed line horizontally until it hits the curve. Okay, from here, okay, we can get another neighborhood, and that neighborhood is neighborhood for n. And that neighborhood of n, look here, the first one is here. I call it n minus b1. The second one is here for the upper bound of the neighborhood of n. We are creating neighborhood of n, yeah? N plus b2. Okay. Now, these two neighborhood, the first neighborhood is this. Okay. The first neighborhood is this. The second neighborhood is this. You can see clearly here, if we try to join this dashed line, then we can create rectangle. Okay, we can create rectangle. And if you could realize that, okay, let me use different color. If you could realize this point and this point are basically the two of the corners of this rectangle, isn't it? And these 2 points are lying on a given curve here. The curve of q equals to function of v. Q as a function of v, yeah? Alright. Now, just imagine if we construct another different neighborhood of L instead of the first one. Let's say here, okay, L minus A3, and then here L plus A4. Draw a dash line again horizontally, then we can get another neighborhood for n. Okay, so let's say here n minus b3, here n plus b4. If we join it, you can get another rectangle. And you can clearly see that this second rectangle is smaller. Okay, so what I'm trying to say is that you can always get different neighborhood for L and N, and you can get smaller and smaller neighborhood, so that it can be verified that for every value of V here in the neighborhood of N, yeah, okay, there is a corresponding value of Q in the neighborhood of L. Okay, all right. Now, what if we deal with step function instead? This one is continuous function. And what if we deal with step function? Can we also analyze it the same way like the way we analyze this graph? What I want you to do is to look at the example of step function analysis for the concept of neighborhood and limit from the textbook. Read it and compare and contrast with the current example that we have in this lecture. Now, we have done the, concept of neighborhood for L, correspondingly for N, using graph. What about if we study it using equations or mathematics? Proper mathematics, yeah? Okay, so let's look at this now. Let's consider this function, and you have seen this function actually in the previous exercise. So let's say Q equals to 1 minus v squared over 1 minus v, such that v cannot be equal to 1, yeah? And I call this equation 1. You must understand why v cannot be equal to 1. If you look here, if v equals to 1, the denominator is always 0, isn't it? And then whatever number divided by 0 is always infinity. So that's why this restriction is there. Okay, anyway. And let's say if we want to find limit of q as v approaches to 1 here. I just jump the step. I don't show you all the steps because this is exercise that you are supposed to do. Then final answer will be equals to 2. So from here we know that this implies we can have n equivalent to 1 from here, yeah? And L here is actually 2, isn't it? Okay. So from here we can create the neighborhood, because let's say we have this answer when v approaches 1, yeah? The limit of q when v approaches 1 is 2. How do we know that answer 2 here is the correct one? In other words, how can we verify that L equals to 2 is actually the limit of Q? How? Alright, so here it is. So let's say for every chosen neighborhood of L, and that neighborhood of L is actually between 2 minus A1 and 2 plus A2. Okay, open interval here. Okay, so this is strict inequality. So for every chosen neighborhood of L written as this, you know how do we get 2 here? Because L here, this is the answer, the limit 2. So we put it here to create the upper bound and lower bound. Okay, so for every chosen neighborhood of L, that is 2 minus A1 and 2 plus A2, okay, 2 plus A2, yeah, this is a mistake here. All right, A2, there exists a neighborhood of N, okay, because L has to be associated with N, so we need to find the neighborhood of N. And what's the neighborhood of N here? The neighborhood of N here is 1 minus B1, 1 plus B2. How do we get 1? Because N here is 1 when limit is 2, isn't it? Okay, so for every chosen neighborhood of L, which is this, there exists a neighborhood of L, which is this, isn't it? All right. So that means, okay, when we have this kind of neighborhood of, L, we have neighborhood of N here, okay, such that whenever V is in neighborhood of N, this is neighborhood of N, whenever V is in this neighborhood of N, that means V must be within this interval, okay, of N, okay. Q must be in the chosen neighborhood of L, isn't it? If V is within this interval, Q must be within this interval also, okay. So from here, for a given value of A1 and also A2, okay, then we must have B1 and also B2, okay, such that we have the following. V must be between 1 minus B1 and also 1 plus B2, but doesn't include these two, okay, with restriction this, because of the earlier restriction here. And also at the same time, okay, Q must be between 2 minus A1 but less than 2 plus A2, okay. So here, let me repeat once again so that you can understand, because here I kept, pausing some bit just because to explain how do you have number 2 here, how do you get number 1 here. So again, our objective is to verify that L equals to 2 is actually the limit of Q, the answer for the limit of Q, okay. So how do we verify it? How do we show it? So here it is. For every chosen neighborhood of L, okay, and this is neighborhood of L, that is between 2 minus A1 and 2 plus A2, okay, there exists a neighborhood of N, okay, that is this one, okay, such that whenever V is in this neighborhood of N, okay, whenever V is in this neighborhood of N, Q must be in this neighborhood of L, isn't it? Okay, so in this case, for a given value of A1 and A2, B1 and B2 must be found, okay, such that, V is between 1 minus B1 and also 1 plus B2, call this equation 2. And also at the same time, Q is greater than 2 minus A1 but less than 2 plus A2. Okay, so we must find number, A1, A2, B1, B2 such that expression 2 here and expression 3 here are satisfied. Okay? Want to find value of B1 and also B2, what we need to do here is that let's say we rewrite equation 3 here by substituting, okay, equation 1 into 3. So this is equation 1 here. Q equals to 1 over 1 minus v square over 1 minus v, such that v is not equal to 1. After you simplify it, then here we have q equals to 1 plus v, isn't it? So this is 1, yeah, such that v cannot be equals to 1. Okay, so we need to substitute it into 3, because we have q here. Substitute q here as 1 plus v. Okay, so what happens here is that it will be like this. So initially we have, 2 minus a1 q2 plus a2, isn't it? Okay, so this is equation 3. Because we have q, after we simplify, we have 1 plus v, such that v is not equal to 1. Okay, so it becomes a what? So this one we can substitute with 1 plus v, becomes 1 plus v instead of q is greater than 2 minus a1, less than 2 plus a2. So let's call this expression 4. And after that, we can actually, bring 1 to the left hand side and also to the right hand side and leave v alone in the middle, yeah, for this. So basically what we are doing is that we want to transform 4 here by subtracting 1 from each side of this inequality. Okay, then it becomes what? So here 2, okay, minus 1 minus a1, isn't it? Then v alone here, 2 minus 1 plus a2, isn't it? Okay, so after that, if we simplify it further, then you can have 1 minus a1, v in the middle, 1 plus a2, isn't it? Now, call this one expression 5. Alright, so here, what we can see is that we have this and also we have this. Okay, so we have two different way of writing. Okay, from here what we need to do is that, okay, we need to find the value of b1 and b2 such that b1 should be equal to a1, okay, and b2 should be equal to a2. Okay, if these two happen, then the two inequality from equation 2 and 3 here will always be satisfied simultaneously, isn't it? Alright, so we have to find b1 equals to a1 and b2 equals to a2 in this case, yeah, after we do all of this, algebra, so that equation 2, sorry, not equation, yeah, inequality 2 and also inequality 3 are satisfied. Now, if this can happen, then what we can say here is that the neighborhood of n, that is, 1 plus, minus b1 and also 1 plus b2, this is the neighborhood of n. I guess required in the definition of limit, yeah, because we use neighborhood concept to explain the concept of limit here. So this neighborhood can be found for the case of L equals to 2. Okay, then we can say that L equals to 2 as the limit. So limit of L equals to 2 exists. Alright, so this is the way we verified the limit of L equals to 2 exists. Now what I want you to do is that try to read textbook on this. In the textbook, there is another way to do it also, the opposite way. Yeah? So I want you to read it. Now, you can try this exercise. So given that q equals to 1 minus v square over 1 minus v, such that v is not equals to 1, okay, try to check the limit of q as v approaches 1 can we say that the limit of q as v approaches 1 is 4? Verify it. So verify it like the way I did it just now. But here, what you can see, I didn't write sentences. Okay. When I don't write sentences here, I explain it to you because this is a lecture. So, but then when you do exercise like this, you have to verify whether, limit of q equals to 4 when v approaches 1 really exists or not. When you verify using all of this explanation that I mentioned to you, you have to write some sentences because if you don't move, how can you see that b1 equals to a1 and b2 equals to a2? I didn't write it, but I did mention, isn't it, by, talking to you just now. So that those things must be put into writing. Otherwise, it's just maths without explanation. Okay, then if it is maths without explanation here, then I don't know whether you have verified that, the limit where L equal to 2 really exists or not for Q equals to this function. All right. So in the textbook, there are a lot of exercises on this. Try to do them. And you can also find some other exercises from the internet and also other mathematical economics textbook. Yeah. And please do them because this is very important. I may ask you in the assignment or in the quizzes also. So we are done with, neighborhood as and its relation to the concept of limit here. We move to the next one here. This is the thing. Digression on inequalities and also absolute values. So I'm sure you have seen this kind of sign when you did your maths in the high school, but let's go into it in detail. Now let's look at the rules of inequalities. Okay. This rule, the first one here is what we call transitivity. And this rule is very, very important. It's not difficult to understand. And it is very useful in the study of economics. Let's look at this rule first. If it is, A greater than B, and if B greater than C, that implies that A is greater than C. Okay? So this is what I said just now. When I say this, it's actually talking about expression 14. When A is greater than B and also B is greater than C, this implies, this sign, arrow sign here means implies, A is greater than C. So this is transitivity, a concept in the study of economics. And this is, if you look at the sign, there is no equality sign. There is no equal sign. That means we have strict inequality. Okay. But if we want to have, weak inequality, then we can rewrite 14 as 15 here. And this is also transitivity concept also. As long as, A greater than B, B greater than C implies A greater, is greater than C. Now, what's the, use of this transitivity concept in the study of economics? One good example to show the concept of transitivity in economics is utility functions. So let's say we have two goods to be consumed, good A and a good B. Okay, so let's say we have the first utility function U1, and then we have U2, and we have U3. All right. So in the graph here, what I can say is that the first thing is utility function 3 is greater than utility function 2, yeah? This is you, yeah? Not me, letter me. Okay, second, I can see that utility function of 2 is greater than utility function of 1. So what does it mean here? From here, it implies that, okay, utility function of 3 must be greater than utility function of 1, isn't it? Therefore, from here, it implies that, okay, U2 here has to be higher than U1, utility function 1, but has to be, lower than utility function of 3. So this one is implied from 1 and 2. So this is the transitivity concept. Okay, I can easily put in equal sign, then it become weak inequality, isn't it? All right. If I don't put equal sign then it becomes strict inequality. All right. So this is the basic idea about the concept of transitivity. Now let's look at the rule of calculation for inequalities and also absolute values after this. Okay, so rule number 1 for inequality says what? If A is greater than B, this implies that A plus minus any constant K should be greater than B plus minus any constant K. K here, value must be the same as K here so that this one can be used. The rule can be utilized. So from 16 here, it implies what? If A is greater than B and B is greater than C, this implies that A plus minus any constant K must be greater than B plus minus any constant K must be greater than C plus minus any constant K. And again, K here value must be the same as here and here. What about the second rule? The second rule is multiplication and division. If A is greater than B, this implies that any constant K times A must be greater than K times B, such that K must be positive. Okay? But any constant K multiplied by A must be less than any constant K multiplied by B as long as K is negative. Now, if you don't understand this, try to put any number to K, let's say 5. And then for this case, K, let's say minus 5. Then you apply this, then you can see, the verification of this. All right, now let's move to rule number 3, squaring. If A is greater than B, such that B must be greater or equal to 0, as long as B is positive or equals to 0, then that means A square must be greater than B square. Is it clear? All right, but this is very easy actually. Now, let's look at the concept of absolute and values and also inequalities. So, let's say usually we write an interval, let's say between minus A and A. And let's say that minus A and A in the form of, numerical value is minus 10 and 10. Is this closed interval or open interval? I did mention to you last time, isn't it? Okay. Now, so minus 10 and 10 can also be represented in another form, that is in inequality form. How do we represent it? It is in the form of expression 20. Now, expression 20 says what? Absolute value of x, must be less than 10. So, the symbol of x, and then you see the vertical straight line like this is actually the absolute value of x. So, to put in a generic form here, then for any real number, call it n, the absolute value of n is actually defined as 21. So, here the absolute value of n is, when n is n like this, when n is positive as long as n is greater than 0. The absolute value of n for n minus n if n itself is negative, isn't it? But if it is 0, then n, absolute value of n is this one also. So here, let's say we use exercise here because we want to apply 21. So if n is 12, the absolute value will be what? So if n is 12, then 12 absolute value is actually 12, isn't it? But what if n is minus 12? What will be the absolute value? So if n is minus 12, then absolute value of, minus 12 is what? Equals to minus, in bracket, minus 12 equals to 12. All right? So we will always see, n absolute value is always equal to minus n absolute values, isn't it? So in this case, what we can say is that absolute values of n is actually modulus of n. Okay? So these are the application of this expression. All right. Next thing is, what if, we want to find the value of x when absolute value of x is less than 10 or whatever number, yeah? So this is what I'm talking about. So what is the value of x when absolute value of x is less than 10? What does it mean, yeah? When absolute value of x is actually less than 10. Now, this question actually we have two possibilities to look and analyze. Number one, if x is positive, yeah, then that means x is actually equals to absolute value of x, and it has to be less than positive 10. Now, in this case, which one is correct? Is it x less than 10 or is it x more than 10? You look here. Okay. So that means this one is correct, isn't it? Look at the way I, make conclusion here. X less than 10. But what happens, okay, because I said to you that there are two possibilities. If x is negative, then minus x is actually absolute value of x and must be less than 10, isn't it? Okay. Now you look here. We say minus x is less than 10, isn't it? So which one is correct in this case? X is less than minus 10 or x is greater than minus 10? It is simple. Okay. X greater than minus 10 because you bring minus sign to the other side. So this one is correct. Then you know that x has to be between minus 10 and 10. Okay, so the interval is minus 10, 10, isn't it? Or another way to write it is x absolute value of x is less than 10. That's why this one can be rewritten as this, and this can also be rewritten as this. Okay, so here from point number 1 and point number 2, we can have the following. Look at expression 22. Absolute value of x is less than n implies that x is between minus n also n. Look here, 10. Okay, we use 10 as n value here. And we can also have the following, 23. When absolute value of x is less or equal to n, this implies that x is between minus n or equals to n and also positive n. Now, which one is weak inequalities? Obviously, 23 because it has equal sign. So 22 is actually strict inequality, isn't it? Okay, we are done with this. Why don't you try different types of number and then try to decide using, two possibilities here. Try to decide, what does it mean by this? What does it mean by this? Can we write it in this form or not? Then you have to do exercise like this in order to check it. Okay? All right. Now let's look at the next one. So we have some characters of absolute values that we need to, take into consideration here. And I'm sure this one is not something new for you, but most of the time, sometimes students already forgot it, although they have, studied it when they were in the high school. All right, number 1, absolute value of n plus absolute value of n is greater or equal to m plus n in absolute term. Okay? Absolute value of m multiplied by absolute value of n is greater or equal to m times n in absolute value. Number 3, absolute value of m divided by absolute value of n is actually equals to m over n in absolute term. All right. Now, again, please do a lot of exercises to understand this even more. There are some theorems that are related to limit because it helps us in terms of, calculation. So you must follow this rule so that your calculation is always correct. So let's say here we have, a number of theorems. But before that, what does it mean by theorem? Okay, if you can recall back theory. So if we have a theorem, then it means it's just a statement that has been proven true. Okay. But last time, remember, if you can recall back, I taught you how to do proof. Okay. What is proof? Proof is actually the explanation of why a statement is correct or true. Okay, so let's begin with the first theorem here for limit theorems. So the first theorem here says that if Q equals to AV plus B, Okay, then we can have limit of q as v approaches n is actually a times n plus b. And we remember that a and b are constant. Let's look at the example. Let's say we have q equals to 3v plus 6. So here, we can calculate limit of q as v approaches what? Let's say v approaches 2 is actually equals to limit of 3v plus 6 as v approaches 2. If we simplify it further, then we can substitute v, with the value of 2 here, and then plus 6. Then finally you get 12. Okay, you do it one by one like this. Don't jump the step, especially this step when you do limit, because you don't just easily substitute the number into it. Yeah. Okay, now let's crack on. So let's say we have theorem number 2. If q as a function of v equal to b, okay, and b is actually a constant, the limit of q as v approaches n is b, not n. Okay, because it's a constant. So let's say we have example here, q equals to 3. So limit of q as v approaches 1, for instance, is always 3. Okay, it's not 1 because you don't find v attached to 3 here. Alright, now next is theorem number 3. If q is equal to v, then limit of q as v approaches n is always n. And if q is equal to v to the power of k, then limit of q as v approaches n is actually n to the power of k, isn't it? This is the final answer, yeah? So let's say we look at example q equals to v square. So step by step, limit of q as v approaches, let's say certain number 2, okay? Then it becomes limit of v square as v approaches 2, isn't it? Then it becomes, substitute v with 2 here, then to the power of 2, then we have 4. Do it step by step. Alright, so that is theorem number 3. Now, let's look at theorem, the next theorem here. But the next theorem here, we have to put certain, condition first, or certain statement first before we can apply these two theorems. Okay, now, we are talking about theorems involving two functions. So let's say we have two functions that have the same variable. That variable is v. So the first one is q1 as a function of v. And also we can have q2 as a function of v. Let's say these two possess the same limit. Okay, so in particular, limit of q1 as v approaches n is L1. Limit of q2 as v approaches, n is L2. Remember, they possess the same limit. That means, L1 and L2 give you the same answer, isn't it? So from here, the following theorems are applicable. Theorem 4, sum or difference limit theorem. So theorem 4 says what? Limit of q1 plus minus q2 as v approaches n is actually the answer for limit q1 plus minus the answer for limit q2. That is L1 plus minus L2. Okay, so the limit of sum of the two functions is the sum of their respective limits, and the limit of difference of two functions is the difference of their respective limit. For instance, if we have this, what is the limit of 2q1 as v approaches n? Now you look here, limit of 2q1 as v approaches n, you can see that 2q1 is actually limit of q1 plus q1, isn't it? That's why it becomes 2q1 as v approaches n. Because limit of q1 is L1, limit of q1 here is also L1. We have two different functions but give you the same limit. Therefore, it gives you L1 plus L1 equals to 2 L1. Alright? Now, if we have theorem number 5 here, theorem number 5 also involves two functions because we have q1, q2. 2q1 here also involves two functions because you have the first function q1 and also the second function q1. q1 and q1 gives you the same limit, L1. Now let's go to the 5 here, yeah? Okay, 5 here example. Let's see, I need to erase some area here so that I can have some space when I write. Okay, so let's see this. Okay, so let's look at the example. Let's say we have limit of q square as v approaches n. Okay, then it can be rewritten as, limit of q1 times, q2 or q1 itself, okay, because it's double here. And we know that the answer for these two limits possess the same answer. Okay, as v approaches n is actually what? L1 is the answer for limit of q1 times L2 is the answer for limit of q2. Then you have L1, L2. That's it. Okay, and then another theorem that involves two functions is this. Theorem number 6, quotient limit theorem. This one is very easy also. Limit of q1 divided by q2 as v approaches n is nothing else but L1 over L2 such that L2 cannot be 0. If L2 is 0, then you get answer infinity, which we don't want to see. Alright? Now, for instance, let's say we have this. Limit of 1 plus v over 2 plus v as v approaches 0. We have two functions here. The first one is 1 plus v. The second one is 2 plus v. So we can find these two limits separately. Okay, so limit of 1 plus v as v approaches 0 is actually equivalent to what? 1 plus 0 equals to 1, isn't it? Limit of 2 plus v as v approaches 0 is what? Is 2 plus 0 is actually 2. Therefore, here we can say that limit of 1 plus v over 2 plus v as v approaches 0 is what? It's actually 1 over 2 or 1/2. What about if we have limit of a polynomial function? Remember, polynomial function consists of, function in which you can see the power is very high or, at least, 2 here. Okay? Not just 1. So how to find the limit of the above function? Then you can see that in this, expression here, you have first function, second function, third, so on and so forth. So we know that limit of a naught as v approaches n is a naught, not n. Why? Because a naught itself is a constant. If we look at the second one here, limit of a1v as v approaches n is what? a1n, isn't it, if I simplify it? And also limit of a2v square as v approaches n is actually a2n square, isn't it? So here, given this kind of polynomial function, then the limit of this function is what? I can rewrite it here. So the limit of q as v approaches n is actually equivalent to a naught plus a1 n1 plus a2 n square plus until the last one a n to the power of n. So this is the limit of polynomial function. Okay, so those are the theorem that you can utilize in the study of limit and also its concept. Now I want to move to the next one, we are still in the study of, continuity and also differentiability and also limit. We want to be more specific here, continuity and differentiability of a function. We have the concepts that we need to look at, but first we look at continuity. Yeah? So when we talk about continuity of a function, let's say we have a function, call it q as a function of v. Okay, so here we have q as a function of v. Okay, now this function we can say that it is continuous at point n. Okay, if this function has limit, as v approaches n. Okay, and as v approaches n, okay, then this function has a limit, and then this limit must be equal to this also. If it's not equal, okay, then we say that it's not continuous. Now, when this function equals to the limit, then we can say that v is actually n, isn't it? So, what's the conditions of continuity that we need to, emphasize here? There are three different continuity conditions. The first one is that point n that we are talking about must be in the domain of the function of g and n. So for instance, if we have a function, okay, and then we see that, v has to be between, 0 and, let's say, 10, but when your n here, for particular v, your n here is, let's say, minus 10, then it is not in the domain, isn't it? Okay, now the second thing is that at point n here, limit of g as a limit of, function v here, q as a function of v here, as v approaches n must exist. That means the limit on the left hand side and also on the right hand side must exist and, equals to certain value, let's say L. Okay, and then that limit, number 3, is actually, as v approaches n, is function of n. Okay, so let's check the existence of limit using the graph that you have learned before. The graph that we have used to learn this is are basically this. Okay, so we have 4 different graphs, this one and this. Let's look at the first one here. You look at particular value that, let's say I use different pen, I use pen, right pen here. You look at particular value of n here, okay, this particular value of n. You look at the curve drawn, this is the curve drawn from here to here, isn't it? And you can see that n is within the, the interval of this curve. Therefore, condition number 1 is met, that is n is in the domain. Okay, n is in the domain. And then next, you see q here. This q has limit at n when v is, at n. Yes, q has limit because we know that from, from left to right and also right of, v here, we have n. That means from left and right, we have L also. Okay, so here q has limit. And then number 3, if q has limit here, does the limit here equals to the function q as a function of v? Okay, yes, because when v approaches, n here, okay, q that we get here is n. Okay, and here that means, okay, L here is a function of n, isn't it? When v is n, you get what I mean here? So it exists and this is the limit. Okay, so 3 condition has been fulfilled for the first graph here. So the function here is continuous when the limit exists for graph A. Now, let's look at graph B. Okay, look at n is here. Look at the curve. The curve is this that has king at, n. And you can see that the first thing here is n is within the domain. Okay, number 1, n is within the domain. So the condition here has been fulfilled for the first condition for continuity. But then, does, q here has limit? Yes, q here has limit as n approaches, as v approaches n from left and right, then we can have limit here, which is n. Okay? Now, so limit is L. And this limit of L here is a function of n. So we know that q as a function of v as v approaches n. Okay, when we talk about limit, yeah. So limit of q as v approaches n is what? Is L. And this one here is actually limit of gn, isn't it? Okay, so it exists. Alright? And the value is this. Okay, so 3 different conditions has been fulfilled. Remember, I haven't talked about differentiability. Continuity concept is discussed here, not differentiability. Okay, so these 2 graphs shows us that continuity exists. Okay, after we check the 3 conditions. Now, let's look at the third graph, graph C. Okay, we have step function. But if you look at n here, what happens? Any value of v below n, okay, between 0 and n, step function here gives us limit L1. Any value of v above n, step function here gives us limit equals to 2. Okay? And very obvious, L1 is not equals to L2, isn't it? Therefore, the limit doesn't exist here because L1 not equal to L2, but from left and right, of n, it doesn't give you the same answer for limit. Therefore, limit doesn't exist. When limit doesn't exist, this violates the condition of continuity in the first place. Okay? N exists. Okay? N is in the domain. But then, okay, condition number 1 is fulfilled. But condition number 2 and 3 are not fulfilled because the limit doesn't exist. Therefore, there is no limit. You get what I mean here? Okay? Now, it only becomes continuous in the interval of this, yeah? 0 and n, the graph is continuous, can you see? And then after that, n until infinity, graph is continuous. But at n itself, okay, graph discontinuous. At n itself, graph discontinuous. That's why you have step at n, okay? And that's why at n, the limit here from left to right is different. You have L1 not equal to L2. Okay? So the graph is discontinuous and the conditions are not fulfilled. Let's look at the last graph here. At v equals to n at this point, okay? Can we say that, n is in the domain? You look at the first curve here on the left side. N is here, but the curve is somewhere here, to the left of N. And you look at the curve on the right side of N is here, but the curve is here. You get what I mean? Okay, the curve is here, N is somewhere here. So N, number 1, is not in the domain at all. Then this violates the continuity requirement. Okay? And because of that, of course, the limit becomes different from the left and also the right side of, v here, n here. You can see this one because we have discussed the limit here, yeah? So you can see the limit doesn't exist at n, but to the left of the limit, it exists, which is minus infinity. To the right, infinity. But at n itself, no answer because minus infinity not equals to infinity, no limit. Then the continuity requirements or conditions are not fulfilled. Alright? So this is how we look at it in the form of a graph. And what about if we talk about, continuity of polynomial and also rational functions? So if we talk about continuity of polynomial and also rational function here, okay? So let's say we have polynomial functions such as this. Q is a function of v, specifically a0 plus a1v plus, a2v square plus until the last one, a n v to the power of n. Okay? We did exercise for this just now, isn't it? Remember when you need to find limit of a0 as v approaches, let's say n, its answer is a0, isn't it? And you have limit of a1v as v approaches n is actually a1n, isn't it? And so on and so forth. When you sum all of them, then you get the answer like I showed you, few minutes ago. Then that means, okay, the limit of this function, polynomial functions, exists at n, and n itself is within the domain, okay, and the limit is basically equivalent to function of v, okay. So this shows that any polynomial function is continuous at its domain. Now, what about rational function? Remember rational function, let me erase this bit first, yeah? When we talk about rational function, it's a function with ratio. Okay, so you have numerator and denominator. Okay, so let's say I have q as a function of v. Okay, specifically we have 4v squared over v squared plus 1. Okay, can we say that, this function defined for all real number or not? What's the domain? Because regardless what happens to v value here, okay, you still have number here, isn't it? Even if v is 0, you still have number on the denominator. Okay, so it has a domain between minus infinity and positive infinity. Okay, so that's the first thing that we can see. It has domain. Okay, so if we put any value of v, let's call it n is within the domain, isn't it? Because n is a constant value. Alright, so n is in the domain. Okay, now, does this function, can we say this function has limit or not? Okay, so limit of q as v approaches n, yeah? You see we have two functions. The first one is this, and the second one is this. It's actually limit of limit of 4v squared as v approaches n over limit of v squared plus 1 as v approaches n, isn't it? Okay. Now in this case, if we simplify, it becomes what? 4n squared square over n squared plus 1, isn't it? And this one, limit of q as v approaches n, is a function of n. You can see n clearly here. Function of n. That means this limit exists and it is exactly the same as a function of n. So 3 requirements are fulfilled for this kind of rational function. Why don't you try some other rational functions and see whether the limit really exists or not? Okay? Now, we are done with the concept of continuity. We need to look at the concept of differentiability of a function. Again, before I talk about differentiability of a function, let me recall back the continuity condition. Yeah. So continuity condition, basically, if I summarize it in the form of formal expression, it can be summarized in the form of 24. If you look at 24 here, limit of function of x as x approaches certain value, let's call that value x naught, is actually as a function of x naught itself. So let's say you have y equals to 5x, right? So if you want to find whether y equals to 5x is a continuous function or not, then you take a limit of y, okay, as x approaches x naught. Let's say x naught here is 1, okay? So here, then it becomes limit of x approaches 1, isn't it? And then we have 5x equals to what? 5, you put 1 here, x naught here is 1. Then you get a limit. So you get a number here. Then it is continuous. So you can see this number 5 is actually a function of x naught, isn't it? That's what it means. Alright? Now, the next thing that we want to see is that, remember, we want to look at the differentiability of a function. So we want to apply limit concept to the difference quotient. And in fact, we have done this before. So let me recall back. If you have this, okay, this is what we call difference quotient. But if you have limit of difference quotient as change in x approaches 0, okay, equals to 1, then this is not difference quotient. The limit of difference quotient is actually, the process of differentiation itself. Okay, so here, what's the link between, difference quotient, limit of difference quotient, and also differentiation? If we are given a function, call it function f or y as a function of x or whatever function, okay, we want to know if, in this function there is a number of x, call it x naught, yeah. So if I put it in the form of graph, for instance, x is here, y is here. So this is a function of x, y equals to fx, okay. Pick one value of x, call it x naught, okay. We want to know at this particular value of x naught, the curve is at this point, isn't it? Okay, it is at this point on this curve, the curve of y or fx, yeah. We want to know at this particular point, can we say that this curve is continuous at this particular point? Okay, in other words, we want to know whether the function f is differentiable or not only continuous but differentiable. All right. Now, if it is continuous, it's very obvious here, it is continuous, but is it differentiable or not? Okay. So, in other words, we want to know whether the derivative dy dx exists at x naught here. We know that based on the graph here, it is continuous. You already know how to check it by checking the limit. Okay, but then at the same time, we want to know whether it is differentiable or not. Now, the differentiability condition of any function actually can be formalized in, a very, formal expression like this. All right. Now, before we go into the detail of mathematics, okay, I want to emphasize on these things so that you can always remember this concept when we go through the steps of, showing the relationship between continuity and differentiability. Okay, continuity and differentiability of a function are related to each other. Now, to be differentiable, a function must be continuous. Otherwise, we cannot differentiate it. Okay, for instance, like I said earlier, if you have step function like this, it's very obvious that you cannot differentiate it, isn't it? But if we have continuity like this or like this, perhaps it can be differentiated or not. That is another issue. All right. But here, we want to see the relationship between continuity and also differentiability. So here, we know that formally, okay, all right, now a particular value of x naught, okay, limit of fx as x approaches x naught is fx naught. This is what I mentioned to you just now. Let me rewrite again expression 20, this one, 24 here, okay. So let's say I rewrite it again here, 24, right? So limit of fx as x approaches x naught equals to fx naught. All right. Now, let's say here I want to replace x naught with n. Okay, replace. All right. Also, I want to replace, x naught plus change in x here, replace it with x. Okay, right. Now, in this case, you look here, x naught is replaced with n. So we can rewrite 24 as this here, limit of fx. Okay, we replace this first. Okay, as x approaches n. Okay, it's actually f n, isn't it? Okay, now this I call it 24a, right? We also learned that, okay, limit of difference quotient can be rewritten as, 25 here. I'm not talking about this. I'm talking about the right hand side, yeah? And I'm sure you have seen this before. And at the same time, I did mention to you previously, limit of difference quotient on the right hand side of 25 here. This is equal sign, the right hand side, yeah? I'm talking about the right hand side of equal sign is actually the derivative, isn't it? Okay, and derivative, we can rewrite it, we can write the symbol like this. We can have it like this. We can have it dy dx, isn't it? We can have it, y prime or whatever it is. Now, anyway, so if you could recall back just now, I did mention to you this. Okay, we want to replace x naught with n. We want to replace change in x plus x naught with x. That means, okay, now let me rewrite again this function because we want to transform it into this. All right. So for this function here, if I rewrite it again here, then f prime x naught, okay, at a particular x naught on a curve, we want to see whether the curve at that value of x, which is x naught, can be differentiated or not. We know that it is continuous, but is it, possible to differentiate it? So here, differentiability sign looks like this. It is actually, like I said in the previous study, the limit of difference quotient as a change in x approaches 0. If I were to write it specifically, it becomes this. Limit of, if you can recall back this, yeah, fx naught plus change in x minus fx naught, isn't it? Okay. Divided by change in x, isn't it? As change in x approaches 0. Alright. Now, because like I said to you, we replace x naught with n, we replace change in x plus x naught with x here. Therefore, you can clearly see that, look at this. Okay, so let me rewrite it again here. Change in x plus x naught, we simply say that it is x. That means from here we can, modify it. Change in x plus n is actually x, isn't it? Remember, because we replace x naught with n. And from here, we can further modify it, becomes, okay, this implies change in x is actually x minus n, isn't it? All right. So I hope this is clear up to this point, yeah? Okay. So now, as you can see, you look here, we want to check differentiability of a function at x naught, isn't it? And the differentiability condition is written as this, isn't it? Now, because we have replaced x naught with n, change in x plus x naught with x here, so basically we can rewrite this as the following. Okay, so you have here f prime x naught become f prime n. Okay, now limit, okay, you see here change in x is equal to x minus n. Okay, but at particular x naught here, we want to make sure that the change in x here as it approaches 0 here, what does it mean here, class? The change in x as it approaches 0 means this one becomes nearer in terms of value to this one, isn't it? You get what I mean? So that means x is approaching n. Almost the same. If it is almost the same, then, the change in x, the difference becomes almost 0. Do you get what I mean? So here, instead of writing change in x approaches 0, we can replace it as x approaches n. As x approaches n, the difference becomes smaller and smaller and approximated to 0. Okay? So here, this one, this bit is replaced by this. X approaches n. Okay? Now, so we have done this bit. Now we want to replace this and this. This becomes very easy already. Because we know that x naught plus change in x is actually x, when we replace it, then here it becomes fx. minus this one becomes Fn. Okay, divided by, what is change in x? Like I said to you, change in x here is almost, 0, but not exactly equal to 0, yeah? That's why, change in x here is equal to x minus n. So here, x minus n, we replace it with x minus m. Okay. Now, before I proceed, I want to show you this replacement in the form of graph. Now, in the form of graph, we know that the original function is y as a function of x. We want to check differentiability, so that's why we do this. Yeah, like I told you in the previous slide. Yeah. So let's say y is here, x is here. Let's say the curve looks like this for simplicity. So this one is y as a function of x. Pick one point, okay, and call it x naught. At x naught, we have, value of y, which is fx naught, okay? And then, if we move to another point, which is here, then we can have the second point, call it x, or before we replace it with x, it's actually x naught plus change in x, isn't it? Because this is change in x, okay? Which is equivalent to this also, isn't it? So here, at this particular value of x, or x naught plus change in x, then we have particular value of y, which is f x naught plus change in x, or we replace it by fx here. X naught here, we replace it by n. Do you get me? So here is actually change in y. Our main focus here is to check whether at particular point of x naught here, is it differentiable or not? So that means we must understand that the change in x here becomes smaller and smaller, so that x here approaches n, or x naught. You get what I mean? At this particular point, at this tangent line, is it differentiated or not? Can we differentiate it or not? Is it differentiable or not? So we want to check, yeah, differentiability. Then that means x must approach n here, so that change in x is smaller and smaller and leads to almost 0. That's the idea behind it. Okay, I hope you are very clear on this. All right, now let's go back to the calculus. So what I did mention to you earlier is that we have continuity condition, which is this, okay, which is in 24a. Also, I did mention to you just now about differentiability condition, which is this, but because of the replacement of x naught with n and changing x plus x naught with x, then the differentiability condition can be rewritten as this. All right, now let's call this one 24b. Okay, what I want to show here is actually the continuity condition here follows the differentiability condition here. Okay, so like I mentioned to you just now, yeah, x approaches n, okay, so that change in x approaches 0, isn't it? Because here, you can see here, change in x is actually the difference between x minus n. But then when we talk about approaches, it doesn't mean that x equal to n. No, it just approaches n. Why we have to emphasize on this? So that when x approaches n is, is not equal to 0. That is very important, yeah? When this is not equal to 0, then it allows us to write something like this, yeah? Now, you look here. Then we can have something like this. Okay, so look here. I put identical sign here. Okay, then I rewrite the right hand side of 24b as this fx minus fn. over x minus n. Okay, now you look here. I'm talking about this, yeah? I'm talking about this. Okay. Now, because x is not exactly equal to n, therefore the difference between x and n is non-zero. Okay, it has to be positive or non-zero. Yeah, because of positive or negative or whatever value, as long as the difference exists. All right. Now, then the thing that I have circled here, I put it back here, and if I write on the left hand side like this, fx minus fn, okay, then what should I do on the right hand side so that the left hand side is equals to the right hand side? Then the right hand side here, I should put x minus n, so this one can be cancelled with this, isn't it? Then they are equal, but I leave it like that because remember, I want to explain, the continuity condition follows from the differentiability condition. Okay, so here, by having x approaches n implies that x is not equals to n, yeah? So that x minus n is, not zero, isn't it? Then, this allow us to write this kind of identity, all right? So, this kind of identity is actually equation 26, okay? Now, from here, so let me rewrite again the number. This is expression or equation 26. We have the left hand side and also the right hand side. So if we take the limit, taking the limit of each side, left hand side and also right hand side as x approaches n, okay, then here, the first thing, I'll take the limit on the left hand side here. So left side, okay. So actually here, it is the limit of fx as x approaches n minus the limit of fn as x approaches n, isn't it? Okay. If you can see here, what have I done when I take the limit? What theorem I followed? It's basically difference limit theorem. Now, you look at this. I use different color now. Limit of fn as x approaches n is what? Because this is a constant, therefore, it is, fn. Okay, then here can be rewritten as limit of fx as x approaches n, this one no change. And then after that, this becomes fn. Okay, because fn itself is a constant. Now, what about the right side? Okay, right side. This is the right side, the right hand side. So when take the limit here, limit of fx minus fn divided by x minus n as x approaches n, and then multiply by the limit of x minus n as x approaches n, isn't it? So you can see here what kind of limit theorem we are applying. This is actually product limit theorem. Okay. Now, from here, what can we do is that if you could realize this, let me use a blue pen. This one. Have you seen this before? I'm sure you have seen this before in this, slide. Okay. Or I would say this one. Okay, after simplification. 24b. Okay, 24b. This is after simplification. So basically, the one that you saw just now is actually f prime n. Okay, let's go back to this. So we can write this bit as f prime n instead, and then multiply by this limit. Okay, this limit. So this limit can be rewritten as limit of x as x approaches n minus limit of, n as x approaches n, equal sign. Okay, right. Now, from here, I can rewrite it as f prime n. Okay. Now look at the one in the circle bracket here. Limit of x as x approaches n becomes what? Becomes n. Limit of n as x approaches n, this is a constant n minus n. Okay. So we are done with the left hand side and also the right hand side. And then you can see clearly that n minus n is 0, isn't it? F prime n times 0, then equals to 0. Now, the left hand side limit is this. The right hand side limit is this. Okay. Here, we cannot write this kind of results. Okay. If this condition 24b is not spelled out just now, isn't it? Because if this one doesn't exist, f prime n doesn't exist, then what happens to the right hand side here? The right hand side here doesn't exist, isn't it? And when it doesn't exist, the right hand side here doesn't exist because f prime n doesn't exist, then what does it mean? Limit doesn't exist, isn't it? It would not possess a limit. So, because f prime n exists here, does exist, then left hand side and right hand side have limits. Okay, have limits. So here, from here we can show this. Let me again rewrite left hand side limit is actually this, yeah? Limit of f(x) as x approaches n minus fn. Okay, and on the right hand side, the final answer that we get is f prime n times n minus n equals to 0. Alright, now equate these two back because this is the condition that we have earlier in 26, isn't it? So we have done the limit, equate both of them back because if in 26 they are equal, limit must be equal as well. Alright, now so equate both of them. Then we have limit f(x) as x approaches n minus fn is actually equals to f prime n. Okay, f prime n times n minus n, or in other words, it can be rewritten as limit of f(x) as x approaches n minus fn equals to 0, isn't it? Because this one equals to 0. Okay. Now, when the left hand side is equated to the right hand side here and the results are the same, then from here we can rewrite it this way. Limit of f(x) as x approaches n equals to fn. Now class, have you seen this expression before? What does it mean by this expression? I'm sure you have seen this. This is actually 24a. What is 24a? 24a is actually continuity conditions. So here what I did was, using differentiability condition, I tried to show that the continuity condition here follows from this differentiability condition. How did I show you? I did say to you that because of this expression and some other conditions that and also some other restriction that I put earlier from the beginning, replacement and whatnot, I use first continuity condition, and then I have second differentiability condition. From differentiability condition, I come up with something like in 26, okay, and then I take limit of 26 both side, left hand side and also right hand side as x approaches n, okay, until finally I get something like this and then this, okay. From differentiability condition in 26 here, 24b here, I repeat once again, yeah, from 24b here, I use differentiability condition. I come up with 26, okay. From 26 here, I take limit left hand side and also right hand side of 26 as x approaches n until I reach this, okay. So you can see clearly from differentiability condition expression earlier, I can, boil down the expression to continuity conditions. That's why I said to you, I have shown you that the continuity condition that we saw earlier in 24a is actually, the one that follows from differentiability condition. Okay? As long as x approaches n such that x is not equal to n. Okay? So I hope this is clear for you. I understand that this is not easy to understand. Okay? For you at undergraduate level. And it seems like the way you learn mathematical economics is more or less like the students for Bachelor of Economics. What you can see here is that when you learn mathematical economics, I would like to emphasize on this thing that we are not asking you, okay, we are no longer asking you actually on how to differentiate 5x. How to differentiate 5x plus 6. We are not. What we are doing here is we are, showing you the concept of, differentiability, difference quotient, or whatever concept and theorem in mathematics in detail in terms of theory, so that all of this kind of explanation can be used later as tools to explain economic theory. Of course, up to this point, you cannot appreciate all of this explanation until you will use it, when you study for master degree or PhD, or when you need to do research and need to prove it using maths, for instance. Okay, what I can advise you is that if you still don't understand what I've shown you here, watch this video again and again, but at the same time, make sure you have your textbook in front of you when you watch this video. Read the textbook together with this video. Try to get some understanding. The language that I'm currently using is the simplest English language possible so that you can understand the lecture. But in order for you to be able to express all of this understanding in the mathematical language, it is very pertinent for you to read the textbook. It is very, very important. All right. Next, if we look at this expression 27, this is an expression which consists absolute term here and then real number 1 here. Okay, why don't you try at home? Draw this function. It is the exercise from the textbook here. You can see the method shown in the textbook. And then you need to check whether the continuity and differentiability of this function exists or not. You need to check like the way I check for, very generic function like this. All right, so it becomes tedious, isn't it? So that's why you need to really understand this concept in order to do exercise for expression in 27 here. All right, now another thing here is that, okay, don't only depends on the exercise in the textbook here. You can see a lot of exercises on, continuity and differentiability concept on the internet, because mathematical economics is not something new in any university around the world. So you need to check exercises, presented by some of the lecturers from, Western countries especially, and also some, Asian Pacific countries. They put some, notes and also some exercises for you to do this kind of this kind of practice. Now, again, I would like to repeat once again. Yeah, I did mention this statement before we before we look into detail for, all of the concept of differentiability and continuity. Continuity of a function, of course, will lead to differentiability of a function, but is it all the time? The answer is no. Okay, continuity of a function is actually a necessary condition. Okay, but okay, it's not sufficient. Okay, it's not sufficient because you can have continuity function of like this. If you pick x naught here, okay, y here, and let's say here f x naught in it. Then if you check the differentiability here, of course it exists, isn't it? You can see the graph is continuous because you don't see any gap along the curve, isn't it? And basically, it's very simple to understand the concept of continuity in terms of graph. When you draw the graph, you don't lift up the pen like this. This one, you lift up the pen, isn't it? But continuity, let's say x here, this is not x naught, yeah, this is y here. So continuity, let's say something like this. This is continuous as well, isn't it? Pick x naught here. This graph is differentiated or not? So if you know mathematics, you know that this one at x naught is not differentiated at all. Cannot be differentiated at all, yeah? So it's not differentiable. So what does it mean here? Can we say that, continuity is a sufficient condition for differentiability? No, it's just a necessary condition, but it's not sufficient to allow us to differentiate a function at particular value of x, for instance, x naught. Okay, this one continuous but differentiable, but the second one here is not differentiable though continuous. If you have this, not continuous and not differentiable, isn't it? So try to get some exercises from the internet as well as textbook. Let's say this, check the continuity and also differentiability of functions, and then try to do something like this to check whether the continuity and differentiability for each particular function like this hold together. Okay, all right. So that is for this chapter. It's a long chapter, yeah, and it's a very theoretical chapter for maths, and it's really real mathematical economics, not like the one that you saw when you did your business maths anymore. Yeah, all right. So good luck in revision.